In the vast expanse of the universe, stars align for a reason. And if you've just landed here from the edge of curiosity, maybe it's written in your cosmic chart to orbit this channel. Join our constellation of curious minds, because out here, every new subscriber is a new star lighting up our galaxy. Now, let's chart a course through the mysteries of the cosmos, starting with Big Bang. Imagine standing alone on a shore at night. The ocean is calm, so still it mirrors the stars above. No wind, no waves, not even the whisper of your own breath seems to exist. In that moment, time doesn't feel like a river flowing forward. It feels like a frozen lake, endless, silent, and eternal. For most of human history, that's how we saw the cosmos, unchanging, infinite, and always there. The stars were fixed, the heavens were perfect. The universe had no beginning, no end, just being. But what if that silence wasn't eternal? What if, long before stars, before atoms, before even time as we know it, there was nothing, not empty space, not darkness, not cold, just no thing, no space to be empty, no time to measure duration, no laws to govern what could or could not happen, a state so alien to our experience that language itself stumbles trying to describe it. This is where our story begins, not with a bang, but with a question. A question so simple it echoes in every child who's ever looked up at the night sky and asked, where did all this come from? For millennia, that question belonged to myth, to philosophy, to faith. But in the last 100 years, something astonishing happened. Science began to answer it, not with certainty, not with finality, but with evidence, with light, with math that hums like a cosmic tuning fork. And what it revealed was more strange, more beautiful, and more humbling than any ancient tale. Before we talk about fire, expansion, or galaxies, we must confront the weight of the idea itself, that everything, the earth beneath your feet, the air in your lungs, the distant quasars blazing billions of light years away, once did not exist, that there was a first moment, that time had a birthday. This notion shatters our intuition. Our brains evolved to track predators, gather fruit, navigate social bonds, not to conceive of a universe emerging from a state beyond physics. And yet, the clues are written in the sky, in the faintest whispers of radiation, in the very fabric of space, stretching like dough in an oven. Think of it this way. If you could rewind the entire cosmos, every galaxy flying apart, every star cooling, every atom vibrating backward in time, faster and faster, everything would get hotter, denser, closer. Galaxies would merge into clouds of gas. Atoms would break apart into nuclei and electrons. Nuclei would dissolve into quarks and gluons. And eventually, you'd reach a point where the known laws of physics fall silent, where density becomes infinite, where temperature soars beyond comprehension. This is the edge of our understanding, the threshold of the Big Bang. But here's the wonder. We didn't arrive at this idea by staring into a void and guessing. We got here because the universe left footprints. Because light from the edge of time reached our telescopes. Because equations written on chalkboards predicted things we later saw with our own eyes. The Big Bang isn't a theory dreamed up in isolation. It's a story written by the cosmos itself, and we are only now learning to read it. And yet, even as we speak of beginnings, we must tread carefully. The phrase Big Bang is misleading. It wasn't an explosion in space. It was the rapid unfolding of space itself, Every point in the universe expanding away from every other point, like raisins in rising bread dough. There was no center, no edge, no outside. The entire universe was smaller than a grain of sand, and yet it was all there was. This chapter isn't about data or dates, it's about awe. It's about standing at the shore of human ignorance and realizing that for the first time in history, we have a map, not of the whole ocean, but of the direction the current flows. We don't know what, if anything, came before the Big Bang. We don't know why there is something rather than nothing. But we do know this: the universe has a history, and that history begins not in myth, but in measurable, observable reality. So let us leave the silence behind. Let us step into the motion, because the sky is not still. It never was. And the story of how we discovered that truth, how we went from believing in an eternal cosmos to witnessing the echo of creation itself, is one of the greatest adventures of the human mind. It starts with a single observation made through a telescope in California that would change everything forever. But before that telescope, there was a man in a patent office scribbling equations that would crack open the nature of space and time. And before him, centuries of stargazers who simply wondered, is the universe alive? Is it growing? Is it dying? We are about to find out. For thousands of years, the night sky was humanity's clock, calendar, and compass. Ancient civilizations tracked the slow dance of planets, mapped constellations into gods and heroes, and believed the stars were fixed jewels embedded in a celestial sphere that turned with perfect, unchanging rhythm. Even as science advanced, Copernicus placing the sun at the center, Newton revealing gravity's invisible hand, the universe remained, in the public imagination, and even in scientific models, static, eternal, unmoving in its grand architecture. The stars might twinkle, but they did not flee. Galaxies, if anyone even knew what those fuzzy patches were thought to be island universes frozen in time. Then, in the early 1900s, everything began to shift, not with a roar, but with a whisper carried on light. It started with a curious observation about color. You've seen it yourself. When an ambulance races past, its siren rises in pitch as it approaches, then drops as it recedes. This is the Doppler effect, and it works with light too. If a star is moving toward us, its light waves get compressed, shifting toward the blue end of the spectrum. If it's moving away, the waves stretch out, turning redder. Astronomers had long used this redshift to measure the motion of stars within our own galaxy. But when they turned their instruments toward those mysterious smudges of light beyond the Milky Way, objects we now call galaxies, they found something baffling. Almost all of them were redshifted. Not just a little, a lot. And the farther away a galaxy appeared, the greater its redshift. At first, this made no sense. Why would nearly every galaxy be racing away from us? It felt suspiciously like placing Earth back at the center of the cosmos, a notion science had worked hard to abandon. But the data kept piling up. In 1923, a young astronomer named Edwin Hubble, working with the most powerful telescope of his time, the 100-inch Hooker telescope, perched high on Mount Wilson in California, made a breakthrough that would rewrite cosmic history. He identified a special kind of star in the Andromeda Nebula, a Cepheid variable, whose brightness pulses in a predictable rhythm. By measuring how dim it appeared, he could calculate its true distance. And what he found stunned the world. Andromeda wasn't a cloud of gas inside our galaxy. It was a galaxy in its own right, 2.5 million light-years away. The universe was vastly larger than anyone had imagined. But Hubble wasn't done. Over the next few years, he and his assistant, Milton Humason, painstakingly measured the distances to dozens of galaxies and compared them to their redshifts. And in 1929, they published a graph that would become one of the most important in all of science. It showed a straight-line relationship. The farther a galaxy was, the faster it was moving away. This wasn't random motion. This was expansion. The entire cosmos was stretching, like the surface of an inflating balloon, with galaxies as dots drawn on its skin, each moving away from every other. Not because they were flying through space, but because space itself was growing between them. Imagine standing on one of those dots. From your perspective, every other dot recedes, and the more distant ones vanish faster. You'd feel like you were at the center, but so would someone on any other dot. There is no center. The expansion is everywhere. This realization shattered the ancient dream of a static universe. The sky wasn't a painted dome. It was alive, dynamic, breathing. Yet even as Hubble's data mounted, many scientists resisted. Albert Einstein himself had earlier introduced a cosmological constant into his equations of general relativity. A fudge factor, he later called it, to force the universe to remain still. When he heard of Hubble's findings, he reportedly said it was the biggest blunder of his life. But the evidence was undeniable. The universe had a history. It had changed. And if it was expanding now, then rewinding time meant it must have been smaller, hotter, denser in the past. This was the first real clue that the cosmos had a beginning, not in philosophy, but in physics. The stars weren't eternal sentinels. They were travelers in an unfolding story. And the redshift wasn't just a shift in color, it was a timestamp. Each photon of light, stretched by the expanding universe over billions of years, carried with it a record of how much space had grown since it was emitted. By reading that stretch, we could, in principle, trace the universe back to its infancy. But who would dare imagine that infancy? Who would propose that all of space, all of matter, all of time itself emerged from a single, searing point? That idea seemed too radical, too close to creation myths, too unscientific. And yet, as Hubble's telescope captured more and more fleeing galaxies, the silence of the static sky gave way to a cosmic hum, a hum that would soon be recognized as the echo of creation itself. The stage was set, the universe was moving, and someone was about to ask, where is it going? And where did it come from? In 1915, while the world burned in the trenches of the Great War, a quiet revolution unfolded not on battlefields, but in the mind of a single man working in a patent office in Bern, Switzerland. Albert Einstein had already upended physics with his theory of special relativity, which revealed that time and space were not absolute. They bent and stretched depending on how fast you moved. But he wasn't satisfied. He sensed a deeper truth, that gravity wasn't a mysterious force reaching across empty space, as Newton had described, but something woven into the very geometry of the universe. What emerged was general relativity, a theory so elegant, so audacious, that it redefined gravity not as a pull, but as a curvature. Imagine placing a heavy ball on a trampoline. The fabric dips. Now roll a marble nearby, it spirals inward, not because the ball pulls it, but because the surface itself is warped. That's gravity, Einstein said. Massive objects like stars and planets warp the fabric of space-time, and everything else, light, planets, even time itself, moves along the curves they create. When Einstein published his field equations, the mathematical heart of general relativity, he didn't just describe how planets orbit. He gave humanity a new language to speak about the entire cosmos. For the first time, the universe could be treated as a single, dynamic entity governed by physical law. And when Einstein applied his equations to the universe as a whole, something strange happened. The math refused to stand still. It demanded motion. Either the universe was expanding or it was collapsing. There was no solution for a static, eternal cosmos. This troubled Einstein deeply. Like nearly everyone else at the time, he believed the universe was unchanging. So, in a move he would later regret, he added a term to his equations, a cosmological constant represented by the Greek letter lambda. This fudge factor acted like a kind of anti-gravity, pushing space outward just enough to balance the inward pull of matter and keep the universe frozen in equilibrium. It was a mathematical patch, not born of observation, but of philosophical preference. But while Einstein hesitated, others dared to follow the math wherever it led. In 1922, a Russian mathematician and meteorologist named Alexander Friedmann, working in near isolation, far from the great centers of physics, solved Einstein's original equations without the cosmological constant. What he found was astonishing. The universe could be expanding, contracting, or even oscillating like a cosmic breath. His solutions described a cosmos in motion, with space itself stretching or shrinking over time. Friedmann published his results, but they were largely ignored. He died just a few years later, never knowing how profoundly he had glimpsed the truth. Then, in 1927, a Belgian priest and physicist named Georges Lemaire, trained in both theology and the latest physics at Cambridge and MIT, rediscovered Friedmann's work independently. But Lemaitre went further. He didn't just accept that the universe was expanding. He asked what that implied about its past. If galaxies are moving apart today, then in the distant past, they must have been closer together. Keep going back, and eventually, all matter, all energy, all space would converge into an unimaginably dense, hot state. A primeval atom, as he called it. From that single point, the universe began to unfold. Lemaitre published his idea in a little-known Belgian journal. Few noticed, but he was undeterred. He saw no conflict between his faith and his science. For him, the Big Bang wasn't a replacement for creation. It was the physical mechanism through which creation occurred. He even corresponded with Einstein, who, upon hearing Lemaitre's hypothesis, reportedly said, "Your calculations are correct, but your physics is abominable." Einstein still clung to the static universe, and yet the equations were speaking a truth louder than preference. General relativity didn't just allow for an expanding universe, it predicted it. The cosmos wasn't a stage where events unfolded. It was an actor in its own drama, growing, evolving, with a history written in the curvature of space-time. The universe had a biography, and the first sentence was being written not in scripture, but in tensor calculus. What made this so revolutionary wasn't just the idea of expansion, it was the implication that time itself had a beginning. In Newton's universe, time was a river flowing forever, independent of what happened within it. But in Einstein's cosmos, time was part of the fabric. If the fabric had a starting point, then time did too. There was no before the Big Bang, not because we lacked data, but because the concept of before requires time to exist, and time began with the universe. This was a philosophical earthquake. For centuries, philosophers from Aristotle to Kant had debated whether the universe was eternal or created. Now, physics was stepping into that arena, not with dogma, but with geometry, the shape of space, the rate of expansion, the fate of galaxies. All could be derived from a few lines of mathematics that described how matter tells space how to curve, and space tells matter how to move. And then, just as Lemaitre was refining his vision, Edwin Hubble pointed his telescope at the heavens and found the redshifts that confirmed the expansion. The equations were no longer abstract, they were etched in starlight. The universe wasn't just theoretically dynamic, it was observably so. Einstein, ever the intellectual, visited Hubble at Mount Wilson in 1931. Standing beneath the great dome of the Hooker telescope, he looked through the eyepiece and saw the evidence with his own eyes. He later admitted his cosmological constant was unnecessary, and perhaps his greatest mistake. But history would have the last laugh. Decades later, we'd discover that the cosmological constant might actually be real, not as a fix for a static universe, but as the mysterious force now called dark energy, accelerating the expansion Lemaitre and Hubble had revealed. The equation that shook reality wasn't just a formula, it was a doorway. It showed us that the universe is not a container, but a process, that space can stretch, that time can begin, that the cosmos has a story, and we are living in its middle chapters. And from that story would emerge not just galaxies and stars, but the very atoms that make up our bodies, forged in the fire of the first moments. But to hear that fire, to feel its warmth across billions of years, we would need more than equations. We would need to listen to the sky itself, and in an unexpected place, amidst radio antennas and pigeon droppings, we would finally hear the echo of creation. In the winter of 1927, a soft-spoken Belgian priest stood before the annual meeting of the Belgian Physical Society and proposed something so radical that even his fellow scientists struggled to grasp its implications. Georges Lemaitre, dressed in his clerical collar but speaking the precise language of mathematics, laid out a vision of the cosmos that defied intuition. The universe had not always existed. It began as an ultra-dense primeval atom, a single point of infinite potential, which then exploded into space, time, matter, and energy. From that fiery origin, everything we see, the stars, the galaxies, the very laws of physics unfolded like petals from a cosmic seed. Lemaitre wasn't a mystic. He held a doctorate in physics from MIT, had studied under Arthur Eddington, the man who first confirmed Einstein's relativity during a solar eclipse, and understood general relativity as deeply as anyone alive. Yet his ideas sounded almost theological. How could science speak of a beginning without invoking a creator? Many dismissed it as poetic speculation. Even Einstein, when Lemaitre presented his theory in person, politely but firmly rejected it. "Your math is fine," he said, "but your physics is abominable." To Einstein, the notion of a sudden origin smacked of creationism, not cosmology. But Lemaitre wasn't trying to prove God. He was following the evidence. He had taken Einstein's equations seriously, more seriously perhaps than Einstein himself, and combined them with the latest astronomical data. He knew about the redshifts observed in distant nebulae. He understood that if galaxies were receding, then reversing time meant they must have once been together. And if all matter was once compressed into a tiny volume, the early universe must have been unimaginably hot. In that heat, he reasoned, the first atomic nuclei would have formed, hydrogen fusing into helium in a primordial alchemy. This wasn't faith, it was prediction. Yet without observational proof, his primeval atom remained a beautiful hypothesis, floating in the realm of theory. What the idea needed was a smoking gun, a signal from the early universe so distinct, so unmistakable, that it could silence skeptics forever. That signal would not come from a priest's notebook or a philosopher's dream. It would come from light itself. Light so ancient, so stretched by time, that it had faded into invisibility. Enter Edwin Hubble. While Lemaitre was refining his cosmology in Leuven, Hubble was perched high in the San Gabriel Mountains of California, peering. Through the 100-inch Hooker telescope, the most powerful eye on the heavens the world had ever known. Night after night, he and his assistant, Milton Humason, measured the distances to galaxies using Cepheid variable stars, those cosmic lighthouses whose rhythmic pulses reveal their true brightness. By comparing apparent brightness to intrinsic brightness, they could calculate distance with remarkable precision. At the same time, they analyzed the spectra of those galaxies, splitting their light into rainbows to measure redshift. What they found was systematic. The farther away a galaxy was, the more its light was shifted toward the red. In 1929, Hubble published his landmark paper showing a linear relationship between distance and velocity. The universe was expanding, not just expanding uniformly, as if space itself was stretching like rising dough. Hubble avoided grand interpretations. He was an observer, not a theorist. He called it the velocity-distance relation, careful not to invoke origins or beginnings. But others saw what it meant. If you ran the cosmic film backward, every galaxy would converge to a single point. Time would compress, temperature would soar. The universe would shrink to a state beyond imagination. Lemaitre read Hubble's results with quiet triumph. He had predicted this. In fact, 2 years earlier, using less precise data, he had already estimated what we now call the Hubble constant, the rate of expansion. His number was rough, but his insight was profound. He even suggested that the expansion implied a finite age for the universe, about 10 billion years, remarkably close to modern estimates. Still, the scientific community remained divided. Prominent astronomers like Harlow Shapley insisted the Milky Way was the entire universe. Those spiral nebulae were just gas clouds within it. Others, like the British astrophysicist Fred Hoyle, championed a rival theory, the steady-state model. In this view, the universe had no beginning and no end. As it expanded, new matter was continuously created to fill the gaps, keeping the overall density constant. It was elegant, eternal, and, as it turned out, wrong. But the debate wouldn't be settled by arguments. It would be settled by listening. Because if Lemaitre was right, if the universe began in a hot, dense state, then that fireball should have left behind a remnant. As the cosmos expanded and cooled, about 380,000 years after the beginning, it would have become transparent for the first time. Before that moment, the universe was a seething fog of charged particles, electrons and protons, so dense that light couldn't travel freely. Photons bounced endlessly, trapped in a luminous prison. But as the temperature dropped to around 3,000 degrees, electrons and protons combined to form neutral hydrogen atoms. Suddenly, light could stream through space unimpeded. That first burst of free-traveling light, the surface of last scattering, should still be reaching us today, stretched by 13 billion years of cosmic expansion from visible light into the faintest whisper of microwaves. Lemaitre never lived to hear it. He died in 1966, just as the evidence was mounting. But others were listening. In 1948, physicists George Gamow, Ralph Alpha, and Robert Herman took Lemaitre's idea further. They calculated that the cooled remnant of the Big Bang should fill the entire sky with a uniform glow at a temperature of about 5 Kelvin, just 5 degrees above absolute zero. It would be the oldest light in existence, a fossil from the infant universe. They published their prediction, but it was largely forgotten. Radio astronomy was in its infancy, and no one had the instruments to detect such a faint signal. Then, in 1964, 2 engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were troubleshooting a sensitive microwave antenna designed for satellite communication. No matter how they cleaned it, removing pigeon droppings, checking for equipment faults, they kept detecting a persistent low-level hiss coming uniformly from every direction in the sky. It wasn't interference. It wasn't noise. It was real, and it matched the predicted temperature of the cosmic background radiation almost exactly. When they heard about Gamo's forgotten prediction, they realized what they had found, the echo of creation, the afterglow of the Big Bang itself. The discovery was electrifying. Overnight, the steady-state model collapsed. The universe had a beginning. It had a history. And that history was written not just in equations or starlight, but in a cold, invisible bath of radiation that had been traveling since time was young. Lemaitre's primeval atom was no longer speculation. It was science. And the priest who dared to imagine a universe with a birthday had been vindicated, not by scripture, but by the silent hum of space itself. The cosmos had spoken, and its first word was light. It began with static. Not the crackle of a dying radio station or the buzz of faulty wiring, but a soft, steady hum that refused to go away. In the spring of 1964, atop a grassy hill in Holmdel, New Jersey, 2 radio astronomers, Arno Penzias and Robert Wilson, were wrestling with a problem they couldn't solve. They had been assigned to calibrate a giant horn-shaped antenna, originally built to bounce signals off orbiting satellites. But no matter how meticulously they tuned the instrument, a faint microwave noise persisted, day and night, coming equally from every direction in the sky. It was as if the entire universe were whispering to them in a language they didn't yet understand. At first, they suspected equipment failure. They checked connections, recalibrated receivers, even climbed inside the horn to scrub away layers of white dielectric grime, left behind, as legend has it, by a pair of nesting pigeons. The birds were eventually relocated, though not before one met a quiet, scientific end. Yet the noise remained. It wasn't local, it wasn't terrestrial, it was cosmic. Penzias, frustrated, called a colleague at Princeton University. There, a team led by physicist Robert Dicke had been actively searching for something extraordinary, the cooled remnant of the Big Bang. Dicke's group had independently revived the idea first proposed by George Gamow and his students 2 decades earlier, that if the universe began in a hot, dense state, it should have left behind a sea of low-energy radiation, stretched by cosmic expansion into the microwave part of the spectrum. They were building a detector to find it. When Penzias described the unexplained hiss, Dicke reportedly turned to his team and said, "Well, boys, we've been scooped. The Bell Labs noise wasn't interference. It was the oldest light in existence, the afterglow of creation itself." What Penzias and Wilson had stumbled upon was the cosmic microwave background, or CMB, a near-perfect bath of radiation filling every cubic centimeter of space, with a temperature of just 2.7 degrees above absolute zero. It is the cooled and stretched echo of the moment the universe became transparent, 380,000 years after the Big Bang, when photons, freed from their prison of charged particles, began their endless journey across the expanding cosmos. This discovery was more than confirmation. It was revelation. For the first time, humanity had touched the infancy of the universe, not through theory alone, but through direct observation. The CMB is a baby picture of the cosmos, imprinted when it was less than 100,000th of its current age. And, like any infant's portrait, it holds clues to everything that would come after. But the true miracle of the CMB isn't just that it exists, it's how perfectly uniform it is. Across the entire sky, its temperature varies by less than 1 part in 100,000. This near-perfect smoothness tells us that the early universe was astonishingly homogeneous, a feature that posed a deep puzzle. If everything was so evenly distributed, how did galaxies, stars, and planets ever form? Gravity needs lumps to work with, slightly denser regions that can pull in more matter over time. A perfectly smooth universe would remain smooth forever. Then, in 1992, NASA's COBE satellite, led by scientists John Mather and George Smoot, detected those lumps, tiny ripples in the CMB temperature, imprinted by quantum fluctuations stretched to cosmic scales during the universe's first fraction of a second. These were the seeds of all structure, the faint imprints of future galaxy clusters, superclusters, and cosmic voids. Smoot famously declared, "If you're religious, it's like seeing God." The media ran with it, but the sentiment was genuine. Here was the blueprint of reality, written in microwaves. Later missions, WMAP and Planck, mapped the CMB with even greater precision, revealing a universe that is 13.8 billion years old, composed of 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB became a cosmic fingerprint, allowing us to measure the universe's geometry, flat to within a fraction of a percent, its composition, and even the rate of its expansion. But perhaps the most poetic truth about the CMB is this: you can hear it. Not with your ears, but with an old analog television. Tuned to an empty channel between stations and about 1% of the static snow you see. The faint white specks dancing on the screen is caused by photons from the Big Bang striking the antenna. Every time you've ever seen TV static, you've been witnessing the afterglow of creation. The universe is literally whispering to you through the noise. This accidental symphony, discovered while cleaning pigeon droppings off a satellite dish, transformed cosmology from speculation into precision science. It silenced the last serious doubters of the Big Bang. It gave us a timeline, a composition, a history. And it reminded us that sometimes the most profound discoveries come not from grand expeditions, but from paying attention to the quiet hum beneath the noise. The CMB is more than data. It is memory. It is the universe remembering its own birth. And as we learn to read its subtle patterns, its peaks and valleys, its polarization swirls, we are not just studying the past. We are listening to the first notes of a cosmic song that is still being written, note by note, galaxy by galaxy, in the expanding dark. In the first moments after the Big Bang, there was no light, no matter as we know it, only energy. A seething, unimaginably hot ocean of pure potential, where the fundamental forces of nature were not yet distinct, and the very concepts of particle and time were still being forged. The universe was smaller than an atom, hotter than the core of any star, and expanding faster than thought could follow. But as it grew, it cooled. And in that cooling, something miraculous happened. The first building blocks of reality began to condense out of the fire. This is the story of the first 3 minutes, the window when the universe transformed from a featureless inferno into a crucible, capable of creating the elements that would one day form stars, planets, and life itself. At 1/10,000th of a second old, the temperature had dropped to about 10 trillion degrees. The universe was now a dense soup of quarks, gluons, electrons, and photons, all dancing in a chaotic ballet governed by quantum laws. But as it expanded further, cooling to about 2 trillion degrees, something profound occurred. Quarks began to bind together. 3 quarks fused into protons and neutrons, the nuclei of future atoms. This phase transition, called hadronization, marked the birth of stable matter. The universe was no longer just energy. It had substance, yet it was still far too hot for those protons and neutrons to stick together. Every time a proton and neutron collided to form a deuteron, the nucleus of heavy hydrogen, the intense radiation would blast it apart. Photons ruled with absolute authority. This era, known as the photon epoch, lasted for nearly 3 full minutes. During this time, the universe was a nuclear prison. Fusion was possible in principle, but impossible in practice. Then, at around 3 minutes and 20 seconds after the Big Bang, the temperature fell to 1 billion degrees, cool enough for deuterons to survive. And in that instant, the floodgates opened. Like a chain reaction in a cosmic forge, deuterons began fusing. 2 deuterons merged to form helium-3. Helium-3 captured a neutron to become tritium, or fused with another deuteron to make helium-4. The stable 2-proton, 2-neutron nucleus that makes up nearly a quarter of all ordinary matter in the universe today. Tiny amounts of lithium and beryllium also formed, but the process stopped there. The universe was expanding too quickly, cooling too fast, to build heavier elements like carbon or oxygen. Those would have to wait for stars. This brief burst of primordial nucleosynthesis lasted only about 17 minutes. By the time the universe was 20 minutes old, the temperature had dropped below 300 million degrees, and nuclear fusion shut down. The elemental recipe was set: roughly 75% hydrogen, 25% helium by mass, and trace amounts about 1 part in 10 billion of lithium. Nothing else. For decades, this prediction seemed untestable. How could we verify what happened in the first minutes of time? But astronomers found a way. They looked to the oldest stars, those born from nearly pristine gas, untouched by later stellar recycling. In the atmospheres of these ancient suns, spectroscopy reveals elemental abundances that match the Big Bang predictions with astonishing precision. The helium fraction, just under 25%. Lithium, vanishingly small but present. Hydrogen, dominant. It's as if the universe kept a receipt from its first chemical transaction, and we finally learned to read it. This agreement between theory and observation is one of the strongest pillars of the Big Bang model. It tells us that the laws of nuclear physics operated the same way 13 billion years ago as they do in laboratories today. That the universe really was once hot and dense enough to cook light elements in its core, and that the matter we're made of, every atom in your body, every drop of water on Earth, traces its lineage back to this fleeting fiery window. But here's the wonder: the universe didn't just make atoms, it made the right atoms. Hydrogen, with its single proton, is the simplest and most abundant element. Perfect fuel for stars. Helium, inert and stable, acts as ash in stellar furnaces, but also as a buffer that helps regulate how stars burn. Without that precise ratio, stars might burn too fast or too slow. Galaxies might not form. Life might never arise. And yet this fine-tuning wasn't designed. It emerged naturally from the expansion rate, the density of matter, and the strength of nuclear forces. All set in the first instance of time. Change any of those slightly and the elemental balance shifts. Too much expansion and no helium forms. Too little, and all hydrogen fuses into helium before stars can ignite. We live in a universe that got it just right, not by intention, but by the elegant interplay of physics and time. After nuclear synthesis ended, the universe entered a long, dark phase. For the next 380,000 years, it was a fog of charged particles, protons, electrons, and light nuclei, bathed in a blinding sea of photons. Light couldn't travel freely. It scattered endlessly off free electrons, like headlights in thick fog. The cosmos was opaque, glowing white-hot, but blind to itself. Then, as the temperature dipped below 3,000 degrees, electrons slowed enough to be captured by nuclei. Neutral atoms formed, mostly hydrogen, some helium, and in that instant the fog lifted. Photons, no longer scattered, streamed freely through space. The universe became transparent. That first light, the moment of decoupling, is what we now detect as the cosmic microwave background. So the journey from fire to atoms was not just a chemical process. It was a transition from chaos to clarity, from unity to structure, from potential to reality. The universe had cooled enough to remember itself. And in that memory, written in the ratios of hydrogen and helium, lies the first chapter of our cosmic story. Not of gods or myths, but of particles, forces, and time unfolding according to laws we can understand. We are made of stardust, yes, but before stars, there was fire. And before fire, there was nothing. The fact that we exist at all is a testament to those first 3 minutes when the universe learned how to build. After the first light escaped, the moment the universe became transparent, it did not blaze with stars. It did not shimmer with galaxies. Instead, it fell into silence. A deep, profound, and almost unimaginable darkness settled over the cosmos, stretching for tens of millions of years. This was the great cosmic dark age, the time between the fading of the primordial fire and the birth of the first star. It is the longest gap in the universe's biography. A chapter written in absence, where nothing shone, nothing burned, and nothing, as far as we can tell, made a sound. Imagine the scene. The universe is now about 380,000 years old. The once blinding fog of plasma has cleared. Neutral hydrogen and helium atoms drift through space, cool and calm, like dust motes in an empty cathedral. The glow of the Big Bang, the cosmic microwave background, has already begun its long fade into microwaves, invisible to any eye. There are no stars, no planets, no black holes, just gas, expanding, cooling, and waiting. This era is called dark, not just because there was no light, but because it is nearly invisible to us. Light is our primary tool for seeing the past. Every photon that reaches our telescopes is a messenger from a distant time. But during the Dark Age, there were no luminous sources to send those messengers. The universe was transparent, yes, but empty of beacons. It was like trying to read a book written in invisible ink. And yet, something was happening beneath the surface. Gravity, the universe's quiet architect, was at work. Remember those tiny ripples in the cosmic microwave background? The 1 part in 100,000 fluctuations detected by COB and Planck. Those were not random noise. They were imprints of slightly denser regions in the early gas, seeded by quantum fluctuations stretched to cosmic scales during inflation. In these overdense pockets, gravity pulled matter inward ever so slowly. Over millions of years, hydrogen and helium began to clump together, forming vast, diffuse clouds, protogalactic seeds. But forming a star is not easy. Gas must collapse under its own weight, heating up until nuclear fusion ignites in its core. In today's universe, heavy elements like carbon and oxygen help gas cool efficiently, allowing it to fragment into stars. But during the Dark Age, there were no heavy elements, only hydrogen and helium, both poor at radiating away heat. So the first collapsing clouds had to be enormous, hundreds of thousands of times more massive than our Sun, to generate enough pressure and temperature to spark fusion. This meant the first stars, when they finally formed, were likely monsters, brilliant, blue, and short-lived, burning with a ferocity unseen since. But that moment was still far off, for now the universe was patient. It had time, hundreds of millions of years of it. One of the few ways we can probe this dark epoch is through the humble hydrogen atom. Hydrogen has a special trick. Its electron can flip its spin relative to the proton. When it does, it emits a photon with a wavelength of 21 centimeters radio waves, invisible to the eye but detectable by sensitive antennas. In the early universe, these 21 centimeter signals were stretched by cosmic expansion to much longer wavelengths, meters long, placing them in the low-frequency radio band. Astronomers are now building telescopes in remote deserts and on the far side of the moon, places shielded from human-made radio noise, to listen for this faint echo. Projects like the Square Kilometre Array and the Lunar Surface Electromagnetics Experiment aim to map the distribution of hydrogen during the Dark Age, revealing how matter clumped before the first light. It's like trying to hear the breath of a sleeping giant before it wakes. But even this signal is elusive. The early hydrogen wasn't emitting in isolation. It was bathed in the fading glow of the CMB, which at that time was still warm enough in the infrared and radio to influence how hydrogen absorbed or emitted 21 centimeter radiation. The interplay between the CMB and neutral hydrogen created subtle absorption features, a kind of shadow against the cosmic background. In 2018, a team using the EDGES radio antenna claimed to have detected such a signal from when the universe was just 180 million years old, suggesting the gas was colder than expected, possibly hinting at interactions with dark matter. The result remains controversial, but it shows how even the silence of the Dark Age may hold secrets. This era was not truly empty. Dark matter, whatever it is, was already shaping the cosmos. Because it doesn't interact with light, dark matter began clumping long before normal matter could. It formed the vast, invisible scaffolding halos and filaments that guided where gas would eventually gather. Without dark matter's gravitational pull, the first stars might never have formed. The Dark Age was thus a time of hidden architecture, where the universe's true structure was being drawn in lines we cannot see. And then, after perhaps 100 million years of darkness, something changed. In the densest cores of the largest gas clouds, pressure mounted. Temperatures soared past 10 million degrees. And deep in the heart of one of those clouds, somewhere in the infinite expanse, a single proton fused with another. Deuterium formed, then helium, and in that instant, light returned to the universe. The first star had been born. Its light was feeble at first, drowned out by the vastness of space. But it was a spark, and sparks given fuel become fire. The Dark Age was ending. But the universe would not simply light up like a switch. The return of light was a violent, transformative process, one that would rip apart atoms, reionize the cosmos, and forge the galaxies we see today. The next chapter would be written in ultraviolet fire. It began with a single point of fire in an ocean of darkness. Not a gentle glow, but a searing blue-white inferno, hotter, brighter, and more massive than any star we see today. This was no ordinary sun. It was a population 3 star, the first generation of stars in the universe, born from pure hydrogen and helium, untouched by the alchemy of previous stellar lives. And when it ignited, roughly 100 to 200 million years after the Big Bang, it did more than shine. It changed everything. These first stars were titans. Without heavy elements to help gas cool and fragment, the collapsing clouds that formed them had to be enormous, perhaps 100, even 300 times the mass of our Sun. Such stars burned furiously. Their cores reached temperatures of over 100 million degrees, fusing hydrogen into helium at a catastrophic rate. They live fast, die young, and explode with unimaginable violence. Some may have lasted only 2 or 3 million years. Cosmic mayflies in a universe still learning to breathe. But their impact was eternal. Their light was not just visible light. It poured out in torrents of ultraviolet radiation, high-energy photons capable of tearing electrons from atoms. And that's exactly what they did. The universe, since the end of the Dark Age, had been filled with neutral hydrogen, calm, cool, and opaque to certain wavelengths. But as the first stars blazed, their UV rays began to rip through this fog, ionizing hydrogen atoms across vast regions of space. Electrons were stripped away, turning neutral gas back into a plasma. Just as it had been before, the cosmic microwave background was released. This process, called reionization, did not happen all at once. It began around isolated stellar nurseries, like bubbles of ionized gas expanding outward from clusters of massive stars. Over hundreds of millions of years, these bubbles grew and merged until the entire intergalactic medium was once again ionized. By the time the universe was about 1 billion years old, the fog had lifted. Not by cooling as before, but by being blasted apart by starlight. Reionization marked the end of the cosmic dark age and the true dawn of the luminous universe. But it was not a peaceful sunrise. It was a violent awakening. The first stars didn't just illuminate space, they sterilized it. Their radiation heated the surrounding gas, making it harder for smaller stars to form. They polluted the pristine cosmos with the first heavy elements: carbon, oxygen, iron forged in their cores and scattered across space when they died in supernova explosions. These elements became the seeds for the next generation of stars, smaller, longer-lived, and capable of hosting planets. We have never directly observed a population 3 star. They lived and died too early, too far away for even our most powerful telescopes to resolve individually. But we see their legacy. The James Webb Space Telescope, launched in 2021, peers deeper into space and thus further back in time than any instrument before it. In its infrared eyes, galaxies from just a few 100 million years after the Big Bang glow with intense star formation. Some appear surprisingly mature, suggesting that star birth began even earlier than we thought. One of Webb's most stunning discoveries is GN-Z11, a galaxy observed as it was just 400 million years after the Big Bang. It's small, only 1%. The mass of the Milky Way, but it's forming stars at a rate 20 times faster. Its light is redshifted so far into the infrared that it would be invisible to Hubble. Webb sees it because it was built to catch the stretched glow of the first luminous objects. Even more telling are the chemical fingerprints in ancient stars within our own galaxy. Some, like contain almost no iron-only carbon and magnesium. This suggests they formed from gas polluted by a single, low-energy supernova of a first-generation star that collapsed directly into a black hole, spewing only its outer layers. These stellar fossils are time capsules, preserving the elemental output of the universe's first fires. But the first light wasn't just stars. Black holes played a role too. As massive stars died, some collapsed into black holes. In dense regions, these black holes merged or gobbled up gas, growing into monsters. When matter spirals into a black hole, it heats up and emits intense radiation quasars, the brightest objects in the universe. Some of the earliest quasars, seen when the universe was less than 700 million years old, shine with the light of 1 trillion suns. Their ultraviolet glare contributed significantly to reionization, helping to clear the last pockets of neutral hydrogen. The era of first light was chaotic, brilliant, and transformative. It turned a dark, simple universe into a complex, structured one. Galaxies began to assemble, drawn together by dark matter's invisible web. Stars clustered, exploded, and recycled their ashes into new generations. Planets became possible. Life, eventually, became possible. And all of it began with that first spark, a star so massive it defies imagination, burning in a sky that had known only silence for 100 million years. Its light traveled across expanding space, redshifted, dimmed, but never extinguished. Today, that light is part of the faint background glow we detect in infrared and radio waves, a whisper from the dawn. We are the children of that first light. Every atom in our bodies, heavier than helium, was forged in stars that followed those pioneers. But without the ultraviolet fury of the first stars, without their violent reionization of the cosmos, there would be no galaxies, no sun, no Earth. The universe would remain dark, cold, and inert. The return of light was not just illumination, it was creation, ongoing, dynamic, and explosive. And it set the stage for everything that came after: the rise of galaxies, the dance of black holes, and the quiet emergence of a pale blue dot where life would one day look back and wonder how it all began. Look up at the night sky. What do you see? Stars, maybe a few planets, perhaps the hazy band of the Milky Way. But what you don't see is far more important. For every glowing star, for every swirling galaxy, there is something else. Something invisible, intangible, and utterly essential. It doesn't emit light. It doesn't absorb it. It doesn't interact with atoms in any way we can directly sense. And yet, without it, galaxies would fly apart, stars would never have formed, and the universe as we know it would not exist. This is dark matter, the universe's hidden scaffolding. The story of dark matter begins not in deep space, but in the motions of galaxies. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive grouping of galaxies about 300 million light-years away. Using the Doppler effect, he measured how fast the galaxies were moving around the cluster's center. According to Newton's laws, the faster they moved, the more mass must be holding them together through gravity. But when Zwicky added up all the visible matter, the stars, the gas, the dust, he found something shocking. There wasn't nearly enough mass to explain the galaxy's speeds. They should have been flung out into intergalactic space like sparks from a firework. Yet they remained bound. Zwicky concluded that most of the cluster's mass must be invisible, what he called dunkel materie, or dark matter. His idea was largely ignored. Astronomers assumed he'd made a mistake. After all, How could most of the universe be made of something we can't see? Then, in the 1970s, an astronomer named Vera Rubin turned her attention to individual galaxies, spiral galaxies like our own Milky Way. She measured how fast stars orbited the galactic center at different distances. According to Kepler's laws, just as planets farther from the Sun orbit more slowly, stars at the edge of a galaxy should move slower than those near the center. But Rubin found the opposite. Stars at the outskirts were moving just as fast as those near the core. The rotation curves were flat, not falling off as expected. This meant one of two things. Either Newton's laws of gravity break down at galactic scales, or there is far more mass in galaxies than we can see. Mass distributed in a vast, invisible halo extending far beyond the visible stars. Rubin's meticulous observations, repeated across dozens of galaxies, left little doubt. The universe was hiding something. But dark matter isn't just inferred from motion. Its presence is etched into the very structure of the cosmos. Remember the tiny ripples in the cosmic microwave background? Those fluctuations are the seeds of all cosmic structure. But for them to grow into galaxies and clusters, there needed to be something for gravity to pull on, something that didn't interact with light. Ordinary matter, bathed in the intense radiation of the early universe, would have been pushed around by photons, smoothing out clumps before they could grow. Dark matter, unaffected by light, began clumping immediately after the Big Bang, forming gravitational wells into which ordinary matter later flowed once the universe cooled. Computer simulations of cosmic evolution confirm this. When scientists model the universe with only visible matter, they get a smooth, featureless expanse. Nothing like the web of galaxies we observe. But when they include dark matter, about 5 times more of it than ordinary matter, the simulations produce a cosmic web of filaments, clusters, and voids that matches observations with stunning accuracy. The large-scale structure of the universe is a fossil imprint of dark matter's invisible hand. We also see dark matter through gravitational lensing, the bending of light by gravity, predicted by Einstein. When massive objects lie between us and distant galaxies, they warp space-time so much that background light is distorted into arcs and rings. By mapping these distortions, astronomers can reconstruct the distribution of mass, even if it emits no light. In galaxy clusters like the Bullet cluster, where 2 clusters have collided, the visible matter, hot gas, detected by X-rays, lags behind due to electromagnetic friction, while the mass inferred from lensing moves ahead. Clear evidence that most of the mass is collisionless and dark. So what is dark matter? We don't know. But we know what it isn't. It's not black holes. Though primordial ones might contribute a small fraction, it's not clouds of cold gas. Those would absorb or emit light. It's not neutrinos. They move too fast to form the clumpy structures we see. The leading candidate is a hypothetical particle called a WIMP, weakly interacting massive particle, that would interact only through gravity and the weak nuclear force. Decades of experiments deep underground, in ice and in space, have searched for WIMPs. So far, nothing definitive. Other theories propose axions, sterile neutrinos, or even modifications to gravity itself, like modified Newtonian dynamics. But Mond struggles to explain all the evidence, especially the detailed patterns in the cosmic microwave background and the behavior of colliding clusters. Dark matter, as a form of unseen mass, remains the simplest explanation that fits all the data. What's certain is this: dark matter shaped the universe. It provided the gravitational framework for galaxies to form. Without it, the first gas clouds might never have collapsed. Stars might have been rare and scattered. The Milky Way might not exist. And Earth, our fragile oasis, would have no home. Dark matter is the silent partner in the cosmic dance. It doesn't shine, doesn't speak, doesn't touch us, but it holds the stage together. It is the unseen architecture upon which the luminous universe is built, a ghostly skeleton giving form to the stars. And as we peer deeper into the cosmos with telescopes like James Webb and Vera Rubin Observatory, we are not just mapping galaxies. We are tracing the contours of the invisible. We are learning to see the unseen, not by light, but by its absence, its pull, its echo in the motion of stars. The universe's greatest story isn't written only in starlight, it's written in shadows. And in those shadows, we find the hidden hand that made everything possible. For most of the 20th century, cosmologists believed they understood the universe's fate. After the Big Bang, gravity, the great cosmic sculptor, would act as a brake. The mutual attraction of all matter would slow the expansion. Perhaps enough to reverse it someday in a big crunch, or just enough to let the universe coast forever into a cold, dark twilight. The question wasn't whether expansion would slow, it was how much. Then, in the late 1990s, everything changed. Two rival teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, set out to measure the universe's deceleration by observing distant supernovae. They used a special kind, Type 1a supernovae, which occur when a white dwarf star in a binary system pulls so much matter from its companion that it reaches a critical mass and explodes. Because this critical mass is always the same, these explosions have nearly identical peak brightness, making them perfect standard candles for measuring cosmic distances. By comparing how bright these supernovae appeared versus how bright they should be, astronomers could calculate their distance. By measuring their redshift, they could determine how much the universe had expanded since the light was emitted. Together, these gave a history of the expansion rate over billions of years. What they found defied belief. The distant supernovae, those that exploded when the universe was younger, were fainter than expected, not slightly, significantly. This meant they were farther away than predicted by a decelerating universe. The only explanation: the expansion of the universe wasn't slowing down. It was speeding up. Space itself was stretching faster and faster. The discovery sent shockwaves through physics. It was as if you threw a ball into the air, expecting it to slow and fall back down. And instead, it accelerated upward, vanishing into the sky. Something was pushing against gravity, not pulling with it. Something was causing empty space to repel itself. This mysterious force was given a name: dark energy. At first, many suspected error. Perhaps dust was dimming the supernovae. Perhaps Type 1a explosions weren't as uniform in the early universe. But as more data poured in from supernovae, from the cosmic microwave background, from galaxy clustering, the conclusion held: the acceleration was real. In 2011, the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics. But what is dark energy? The simplest answer lies in an old ghost: Einstein's cosmological constant. Recall that in 1915, Einstein added a term, lambda, to his equations to keep the universe static. When Hubble discovered expansion, Einstein called it his biggest blunder. But now, lambda was back, not as a fix for a static cosmos, but as a property of space itself. According to quantum theory, even empty space seethes with virtual particles popping in and out of existence, creating a background energy. the vacuum energy. This energy would exert negative pressure, causing space to expand at an accelerating rate. The problem? When physicists calculate the expected value of this vacuum energy, they get a number 120 orders of magnitude too large. That's a 1 followed by 120 zeros, an absurd mismatch. Either our understanding of quantum fields is deeply flawed, or something else is at work. Alternative theories propose that dark energy isn't constant, but a dynamic field that changes over time, dubbed quintessence. Others suggest that Einstein's theory of gravity breaks down on cosmic scales, and we need a new theory of gravity altogether. But so far, no alternative fits the data as well as the cosmological constant. What we do know is this: dark energy makes up about 68% of the total energy content of the universe. It dominates the cosmos, and its effects are growing. As the universe expands, matter dilutes, but dark energy, being a property of space, stays constant or even increases. That means its influence will only grow stronger over time. The implications for the future are chilling. If acceleration continues, distant galaxies will eventually move away faster than light can cross the gap. They will vanish from our view, not because they cease to exist, but because their light can no longer reach us. In 100 billion years, astronomers in the Milky Way, if any remain, will see only their local group of galaxies. The rest of the universe will have disappeared beyond an event horizon, as if it never existed. The cosmic microwave background will redshift into undetectability. The evidence for the Big Bang itself will be erased. We live in a privileged time, a cosmic sweet spot where the universe is old enough to have formed stars and planets, but young enough that we can still see its history written in light. In the far future, cosmology may become impossible. The story of the Big Bang could be lost, not to ignorance, but to the relentless stretching of space itself. Dark energy is the universe's final plot twist. After gravity-built galaxies, after stars forged elements, after life emerged on a pale blue dot now, the very fabric of reality is pulling itself apart. Not with violence, but with quiet, inexorable expansion. And yet, this acceleration may hold clues to the deepest questions in physics. Why does dark energy have the value it does? Is it connected to the quantum vacuum? To the multiverse? To the nature of time itself? We don't know. But every observation, every supernova, every ripple in the CMB, every map of galaxy distribution brings us closer. The stretching of space isn't just a fate, it's a message. The universe is not only expanding, it's evolving in ways we're only beginning to understand. And in that expansion, we find both our origin and our ultimate solitude. For now, we watch, we measure, we wonder, and as the cosmos accelerates into the dark, we hold tightly to the light we still have, the light that tells us who we are, where we came from, and how briefly, beautifully, we get to know it. We have come far, from the silence before time, through the fire of creation, the dark age of waiting, the blaze of first stars, the invisible hand of dark matter, and the accelerating stretch of space. We have traced the universe's story with astonishing precision. We know its age to within a few million years. We know its composition to within 1%. We can read the ripples in its baby picture and predict the motion of galaxies billions of light years away. And yet, as we stand at the edge of understanding, we find ourselves facing a horizon, not of space, but of knowledge. Beyond it lies mystery, and some of those mysteries may never be crossed. The most profound of these is the very beginning, the singularity. General relativity tells us that if we rewind the expansion, the universe becomes infinitely dense, infinitely hot, where space-time curvature becomes infinite and the laws of physics break down. But infinities in physics are not answers, they are warnings. They tell us that our theories have reached their limits. General relativity, for all its power, does not include quantum mechanics, the rules that govern the very small. And in the first fraction of a second after the Big Bang, the entire universe was smaller than an atom. To understand that moment, we need a theory of quantum gravity, a framework that unifies Einstein's space-time with the probabilistic dance of quantum fields. We do not have such a theory yet. String theory, loop quantum gravity, causal dynamical triangulations. These are candidates, but none have made testable predictions confirmed by observation. Without experimental guidance, they remain beautiful mathematics, not established physics. So the true nature of the beginning, if there was one, remains unknown. This leads to the most haunting question of all. What, if anything, came before the Big Bang? The word before may not even make sense. Time, as we understand it, is part of the universe. It emerged with space in the Big Bang. Asking what happened before, time is like asking what's north of the North Pole. It's a category error, and yet some models suggest alternatives. In loop quantum cosmology, the Big Bang might have been a big bounce, a previous universe collapsing and rebounding. In eternal inflation, our universe could be one bubble in a vast multiverse, constantly spawning new universes with different physical laws. In the no-boundary proposal by Stephen Hawking and James Hartle, the universe has no initial boundary in time. Like the South Pole on Earth, it's a point where time becomes space. These ideas are compelling, but they are not yet science in the strictest sense. They lack direct observational evidence. The multiverse, for instance, may be untestable by definition. If other universes are causally disconnected from ours, we can never observe them. And while some hope that patterns in the cosmic microwave background might reveal collisions with other bubbles, no such signal has been confirmed. Then there is cosmic inflation, the theory that in the first trillionth of a second, the universe underwent a phase of exponential expansion, growing from subatomic to cosmic size in a flash. Inflation elegantly explains why the universe is so flat, so uniform, and why the CMB ripples have the pattern they do. But despite its success, we don't know what drove it. The hypothetical inflaton field remains undetected. And while experiments like BiCP and Planck have searched for primordial gravitational waves, ripples in space-time from inflation that would leave a distinctive swirl in the CMB's polarization, the signal remains elusive, buried under dust from our own galaxy. Even the nature of dark matter and dark energy, comprising 95% of the universe's content, remains unknown. We see their effects, but not their essence. Are they new particles, new fields, or signs that our theory of gravity is incomplete on cosmic scales? Decades of underground detectors, particle colliders, and space telescopes have narrowed the possibilities, but the core mystery endures. And what of the ultimate fate? If dark energy remains constant, the universe will expand forever, growing colder, darker, emptier. A heat death where no work can be done, no stars shine, no life persists. But if dark energy strengthens over time, a scenario called phantom energy, it could rip apart galaxies, stars, planets, and even atoms in a big rip. Or if it weakens, gravity might one day reclaim control. We simply don't know. These are not failures of science. They are its frontiers. Every great discovery opens new questions. Newton's gravity explained the planets, but couldn't account for Mercury's orbit, leading to Einstein. Einstein's relativity revealed the expanding universe, but couldn't describe its quantum birth, leading to the search for quantum gravity. Science advances not by claiming final answers, but by standing humbly at the edge of the unknown and saying, "Let's look closer." And we are looking. The James Webb Space Telescope peers into the epoch of first light. The Vera C. Rubin Observatory will map billions of galaxies to trace dark matter and dark energy. Future missions may detect gravitational waves from the Big Bang itself. Experiments deep underground hunt for dark matter particles. Theories are tested, refined, discarded, reborn. But some questions may remain forever beyond our reach. The observable universe is finite, about 93 billion light-years across, limited by how far light has traveled since the Big Bang. Beyond that cosmic horizon, space may extend infinitely, or curve back on itself, or branch into other universes. We may never know. And yet, there is beauty in the not knowing. The universe does not owe us answers, that it gives us any at all, that we can decode the composition of stars from their light, reconstruct the universe's history from a faint microwave hum, and stand on a tiny rock orbiting an average star and comprehend the cosmos is a miracle of reason and curiosity. The horizon of knowing is not a wall. It is an invitation. It reminds us that wonder is not the enemy of understanding, but its companion. That the most profound scientific journey is not just to explain the universe, but to remain awestruck by it. We may never know what, if anything, caused the Big Bang. We may never see beyond our cosmic horizon. But in asking the questions, in building telescopes, writing equations, listening to the static of creation, we participate in the universe becoming conscious of itself. And perhaps that is enough. Look at your hand, turn it over, feel the pulse in your wrist. That rhythm, the steady beat of your heart, is not just biology, it is cosmology. The iron in your blood, the calcium in your bones, the oxygen in your breath. Every atom heavier than hydrogen and helium was forged in the heart of a star that lived and died billions of years ago. You are not separate from the universe. You are the universe, awake, aware, and looking back at itself. This is the final, most intimate truth of the Big Bang. It did not happen out there, in some distant realm of space and time. It happened everywhere. It happened here. The same fire that filled the cosmos in its first moments cooled, expanded, and evolved into galaxies, stars, planets, and eventually beings who could ask, where did we come from? The story we've traced from the silent beginning through the stretching of space, the Dark Age, the first light, the hidden scaffolding of dark matter, and the accelerating void is not just the history of the cosmos. It is our origin story, not in metaphor, but in measurable fact. Consider the hydrogen in the water you drink. Those atoms were born in the first 3 minutes after the Big Bang. They have existed, unchanged, for 13.8 billion years. They swirled in the primordial gas clouds that collapsed to form the Milky Way. They were part of the molecular cloud that gave birth to our Sun 4.6 billion years ago. They cycled through oceans, atmosphere, and living cells. Perhaps in a dinosaur, a fern, a raindrop, before becoming part of you. The carbon in your DNA? Forged in the core of a red giant star, fused from helium under crushing pressure and heat. The oxygen you breathe, created when massive stars exploded as supernovae, scattering their enriched guts across the galaxy. The gold in jewelry, the iodine in your thyroid, the zinc in your enzymes, all were cooked in stellar furnaces or in the violent mergers of neutron stars. Events so rare and energetic, they happen only a few times per galaxy per million years. You carry the ashes of dead stars in your cells. You are made of recycled starlight. And it's not just your body, your thoughts, your wonder, your capacity to imagine the Big Bang itself. These too are products of cosmic evolution. The laws of physics that allowed atoms to form also allowed complex molecules to self-assemble. The same gravity that pulled gas into galaxies also pulled dust into planets. On at least one of those planets, in a quiet corner of an ordinary galaxy, chemistry became biology, and biology became consciousness. This is not poetry. It is physics, chemistry, astronomy, and biology converging on a single, breathtaking conclusion: we belong here. The universe did not create us as an afterthought. We are one of its natural outcomes, a way for the cosmos to know itself. Think of the journey light takes to reach your eyes. A photon emitted by the sun takes 8 minutes to cross space and strike your retina. But the atoms that made that photon, the hydrogen fusing in the sun's core, were themselves born in the Big Bang. When you feel the warmth of sunlight, you are feeling the echo of creation, filtered through a star. And when you look up at the night sky, you are not just observing distant objects, you are seeing the past. The light from Andromeda left when early humans walked the Earth. The faint glow of the cosmic microwave background has been traveling since before Earth existed. In that light, you are touching the infancy of everything. This connection is why the Big Bang matters, not just to scientists, but to all of us. It dissolves the illusion of separation. It reminds us that we are not visitors on this planet, but participants in a cosmic drama billions of years in the making. Our joys, our sorrows, our questions, they are all part of the universe unfolding. And in that unfolding, we have been given a rare gift, the ability to understand, to build telescopes that see back to the first galaxies, to decode the chemistry of stars from their light, to write equations that describe the birth of time. No other species we know of can do this. We are the universe's way of reflecting on its own story. That story is still being written. Every new discovery, every ripple in space-time, every exoplanet found, every particle detected adds a sentence. And we are the ones writing it, not with divine revelation, but with curiosity, collaboration, and courage. So the next time you feel small beneath the vastness of the night sky, remember, you are not insignificant. You are the universe become conscious. You are stardust that learned to wonder, and in your wondering, the cosmos finds meaning. The Big Bang was not the end of mystery. It was the beginning of a story, one that includes you. And as long as we keep looking up, keep asking questions, keep listening to the static between the stars, that story will continue. Not in silence, but in awe.